All right, hello. So this is recitation, or I guess video recitation for Tuesday, September 15th. The worksheet is posted on Canvas under Week 5 Recitation Worksheet Murphy. The last 5 problems I've already provided, or the last 6 problems, sort of the additional review problems that I had included on that worksheet as to go over in case we got time, already provided walkthroughs for those. So I was just going to go through now the first 3 pages of that worksheet, which I had originally planned for recitation. So my plan is I'm just going to walk through the solutions to each of the problems. I highly encourage you to look at all of these beforehand. And again, if you have any questions on these, please email me. We can set up a time to meet via WebEx and talk about really these problems or anything. So problem number 1, if you're following along on the worksheet, says to consider a rabbit population, P of t, satisfying this logistic equation. So here we've got A times P is the birth rate, and B times P squared is the death rate. So sort of how is the population changing over time. And so we're given then an initial population of rabbits to be 220. So we know that P sub 0 is equal to 220. We're also given the birth rate and the death rate. So we're given that the birth rate is 6, and this means that 6 is equal to, the rate occurring at time 0. So we get 6 births occurring at time 0, which means 6 is equal to A times P sub 0, which is 220. And then deaths, we get that 10 is equal to B times 220 squared. So these are occurring at time 0. We know the population at time 0. And so we want to know how many months does it take for P of t to reach 115% of the limiting population M. So I've got kind of how we're going to work this problem, or the start to this problem on the board. So if we let K equal B and M equal A over B, so here's the limiting population, then we can actually rewrite this logistic equation in this form. And so this should look a little more familiar because this model for population growth, we actually already know the solution to this differential equation. So if we solve this differential equation, we get this model for the population at time t in terms of all of these variables. And so what we want to know the time t when the population has reached 115% of its carrying capacity, meaning when is P of t equal to 1.15 times M. So now we just have to solve for t in the following equation. And I'm going to plug some things in here in a somewhat specific way. So I'm going to plug in 220 for P sub 0 everywhere. This M, I'm actually going to plug in A over B. I'll leave this M alone because I'm going to eventually cancel it, so we get A over B minus 220 times E. So notice negative K times M is equal to negative B times A over B. So this negative K times M in the power of E here can just be simplified to E to the negative AT. So now A over B, well, we know that A is equal to 6 over 220. We know that B is equal to 10 over 220 squared. So this should be 6 over 220 times 220 squared over 10. And so that should be 6 times 220 over 10. And that should be 6 times 22, which is 132. So a over b is equal to 132. So now notice I'm going to simplify this equation a little bit. These two m's cancel out. So I get that 1.15 is equal to 220 over 220 plus 132 minus 220. So that's a over b. And then e to the negative 6 over 220 times t. So at this point, it's just solving for t in this formula. The way I would do this, I think this is the way that kind of makes it as easy as possible. I would move this entire thing up into the numerator. So I'd go 220 plus 132 minus 220 times e to the negative 6 over 220t is equal to 220 divided by 1.15. So sort of swap this and this. Then subtract 220. 132 minus 220 is equal to negative 88. So doing a little bit more algebra here, you should get negative 1 over 88 times 220 over 1.15 minus 220. And then you could take the natural log of both sides and divide, and you should get t is approximately 41.09. I actually don't know how accurate Pearson wants you to be with this number. I know that I had messed up I made some rounding error the first time I did this and got like 40 point something, and it marked me wrong. So in general, what I would do is, especially if you have a graphing calculator, it should be pretty easy to not need to round until the very end, in which case you should always get the correct answer. But I'd say, if you did this and you got anything remotely close, within maybe a tenth to 41.09, you're probably okay. This is just sort of word problem using this logistic growth model for population growth. Now moving into chapter 2, we can actually study this differential equation or differential equations that look a little bit like this a little more to see sort of maybe some more intuition as to why something like this would be a better model for population growth. All right, so hopefully I spliced the two videos together in a sensible way. So this is page 2 of the recitation worksheet. So this, I just wanted to briefly talk about a little bit. I'd planned to talk a little bit about sort of why we care about kind of what we're going to be doing, or what the next two problems cover. So here we've got this differential equation, which actually looks somewhat similar to the previous logistic model that we had looked at last example. And notice that this function does not depend on t at all. And so in this case, we'd call this an autonomous equation because it only depends on the dependent variable x. So that makes drawing slope fields really easy. So I figured we could remind ourselves a little bit about slope fields. Because we really only have to worry about here the x-axis as opposed to the t-axis. So if I want to draw the slope field of this equation, notice at 0, and I'll draw these lines maybe a little above 0 so we can actually see them, that the slope of this equation is 0 because when I plug 0 into my differential equation here, I get a value of 0. When x is equal to 1, 1 times 3 minus 1 is 2, so I get a slightly positive slope, like that. And so notice again, what's nice about this, I don't really have any regard for what t is here. I can just look at x values. Now notice when x is equal to 2, again I get 2 times 1, so I actually get the same slope. So all of these slope dashes are 2. Now when x equals 3, however, I get a slope of 0 again. All right. If I flip above, when x is equal to 4, I would get 4 times 3 minus 4, which is negative 4, so I would get very negative slopes here. And you could probably start to see a trend. When x was equal to 5, I'd also get very negative slopes. My graph is going to look like that. And then going below the x-axis, or the t-axis, excuse me, when x was equal to negative 1, this would be negative 1 times 3 plus 1, so it would also be very negative. And then you could actually continue this and just see that this gets more and more negative the further away I get from 0. So all of these slope dashes will still be negative going down. All right, and so we can sketch a few solution curves. Namely, notice I've got these kind of two horizontal lines above at x equals 3 and at x equals 0. And so notice any solution curve that starts above x equals 3 will do that. Any solution curve that's sort of in the middle of these two will do, I'll basically do that. And then any solution curve below this will do that. So critical points of this equation are the points when, or of equations like this in general, are actually these 2 points where the slopes, or where dx dt, or just f of x here, equals 0. And so here the critical points would be 3 and 0. And so you could kind of see this as like being a good model for population, because notice, like, if you imagine curves like this describing maybe a population in the wild, you could think of x equals 3 maybe, or this sort of a horizontal line somewhere in the positive region, as representing like the carrying capacity. And so anything below this line, if the population starts below this line, it sort of tends to increase until it reaches that carrying capacity. Anything above this line, maybe there are too many members of the population for the environment to support, and it would have to decrease until it hit this line. So if you notice, like, everything sort of in this region here always tends to this critical point of x equals 3. X equals 0, if we start at 0, so if we had a line actually just starting at 0, that line would stay at 0. But notice everything else tends to go away from 0. And so maybe ignoring the idea that we might have a negative population, this also makes sense, that if we start with any amount of population, maybe that population will grow until it reaches the carrying capacity. And so here we'd say that C1 equals 3 is a stable critical point because the graph moves toward 3 when it is around 3. So it's sort of when it's bounded by x equals 0, it's not going to cross this 0 line to get to 3. But if we look at the region surrounding 3, the graph tends to move towards 3. And so here we'd say that's stable. And 0 is unstable. Because graph moves away from 0. So in this way, critical point where the graph is moving towards that point is stable as t approaches infinity. And if we're tending away, so notice even if we start very close to 0, our solution curve will always take us up or down depending on what side of 0 we're on. And so in this way, like the graph, no matter how close we start to 0, will run away from 0 for x equals 3. As long as we start in one of these two regions, then the graph will tend towards 3. So stable is the graph tends towards that critical point. Unstable is the graph veers away from that critical point. So there's actually sort of, you can look at slope fields certainly, and they'll kind of give you an idea as to when this happens. The other way you can do it is looking at these phase diagrams. So if I drew 0 here, 3 here, sort of on a number line, what you could do is you could actually check points. So maybe we'll check x equals 1, x equals -1, and x equals 4. You could actually kind of check the points on either side of these critical points to see what the slopes are doing. So notice when x equals 1, as we already saw, this slope is positive. So the arrows would be pointing away from 0 and into 3. On the other side of 3, the slope was negative. So here we've got the arrow pointing into 3. And then on this side of 0, the slope was also negative, and so we'd have the slope pointing away from 0. So if we're looking at phase diagrams, something that looks like this would be unstable. This would be stable. An example that we won't get to see, but is worth mentioning, if we had something that looked like this, this would be semi-stable. So here you'd have sort of one side of that critical point would be tending towards that line, and the other side would be tending away. So yeah, sort of just a quick walkthrough. If you haven't already, try the other two problems on the worksheet. I think all of this sort of covers what you would need to do to get through them. And then I'll just walk through each of those solutions. And both of those correspond to two homework problems. So here's the setup for the first problem. Now, on this, so these correspond to homework 5, questions 7 and 8. And so you're asked to do a variety of things. So here we want to solve the equations for f of x equals 0 to find the critical points. Next, we want to analyze the sign around those critical points, draw the phase diagrams in order to determine whether or not we've got an unstable or stable critical point. Then we want to actually just solve the differential equation. And then we want to use slope fields to verify the stability of each critical point. And so I have here, you should be able to construct these on your own, again, because this is an autonomous equation. it ends up making it a little easier and a little quicker, that you kind of just need to know what's going on the x-axis and not the t-axis. However, for each of these, since I had originally planned to do this in person, I decided it would just be easier to have the slope fields there for reference. So, critical points. All we want for critical points here with an autonomous equation like this, remember, are all of the points for which x minus 5 is equal to 0. And so notice you'd get one critical point, c1 equals 5. So this actually very much just corresponds to critical points like you would have in calculus. You can actually verify this with the slope field already, that notice the slope here is 0 when x equals 5. So you could verify this with the slope field. However, you might not always have slope fields, so we should draw a phase diagram for this critical point to determine if it is stable or unstable. So remember, with this, what we want to do is take our point and sort of in number line fashion check what's happening on either side of that point. So when x is equal to 6, x minus 5 is positive, so we would get positive slope, so tending away from my critical point. When x is equal to 4, 4 minus 5 is negative, we'd get negative slope, so we're tending in this direction. And so given this phase diagram, remember, basically any point or any solution curve that even starts as close to 5 as we want, but not right at 5, is going to fall off or run away from 5. And so because we get something like this, we'd say that 5 is unstable. And so if you wanted, you could also construct a few solution curves, kind of just draw them in. So if we start below 5, you can see it falls off. I didn't leave myself a ton of room up here, but the slope will just keep increasing. So if we look at the actual curve of this differential equation, then notice it's never actually approaching 5. It's just running away from 5. However, if we started at 5, of course, then it would stay constant at 5. All right, so now we want to solve the equation itself. Thankfully, this is separable. So it's not too bad. I can separate the variables to get 1 over x minus 5 dx is equal to dt. And then I integrate to get natural log of x minus 5 is equal to getting a little ahead of myself there, t plus c. Now we take both sides to the e, and we get that x minus 5 is equal to e to the t plus c. And so solving for x, we would get that x is equal to e to the t plus c plus 5. And so again, looking at the slope field I drew, you could pretty quickly convince yourself that this equation, in fact, is, or that this calculation here is correct, because you can kind of see what's happening. Yeah, we'll move on now to the next homework problem. All right, so last problem on this sheet. Looks very similar, a little more involved, I guess, because we've got now a quadratic equation here. So here we've got dx dt is equal to x squared minus 4. So first thing we want to do, we want to find the critical points. So to do this, we just want to set f of x, or in this case x squared minus 4 equal to 0. This factors as x plus 2 times x minus 2. So that's just difference of squares. And so from this we get x equals 2 and x equals negative 2, which maybe I'll call critical point C1, and critical point C2 are the two critical points of this equation. All right, so I'm going to draw the slope field at the end just to get a little more practice, maybe doing that by hand. Of course, it's on the worksheet, so maybe you can see it, but figured it'd be good to just go through the process once more. So next we want to draw phase diagrams to verify that the solutions we got are correct. Well, not correct. We want to verify. We know that I hope this is correct. We want to verify that these points are either stable or unstable. So maybe first I'll plug in 0 here. So 0 squared minus 4 is negative, meaning here the function is tending in the negative direction. All right. On the left-hand side of negative 2, well, notice that anything bigger, I guess, like if I plugged in negative 3 squared is 9, minus 4 is 5. And so here, everything would be tending in the positive direction, which means that negative 2 is stable. Finally, for positive 2, if I plugged in 3, well, 3 squared is 9, minus 4 is 5, so this is also heading in the positive direction. And this means that 2 is unstable. So remember, the way you check these two things, just check these slopes around the 2 points. So for these, check slopes around critical points using the formula for not dy dx, dx dt. And that should always just tell you sort of the direction of the slope. So this should be very similar to like analyzing critical points back in calculus. All right, so number 3 says to solve the differential equation. I'm going to do that last because we'll need a little more space for that one. So what I'm going to do now is walk through drawing the slope field, and then maybe we'll draw a few solution curves to kind of see that our maybe what we have here is really correct. So since we know 2 and negative 2 are critical points, we immediately know that the slope of my differential equation at all those points is 0. So here's 2. There's negative 2. So now maybe we'll start here. Remember, when I plug in for 3, I get something positive. If I plugged in 4, I would get 16 minus 4, which is 12, which is an even bigger slope than I got when I got 3. So this function is increasing in that way. In between here, if I plug in x equals 1 to this formula, I would get negative 3. x equals 0, I would get negative 4, however, so it's decreasing maybe a little more. But x equals negative 1, I would get 3 again, so it starts to then level off, which is good, because then again it equals 0 at 2. And now here, coming out of 2, it should start to get more and more negative, because it should kind of mirror what's going on up here. So then it should, more and more positive, excuse me. Should be the same slopes that we're getting on the other side of this line. So this actually looks a lot like the logistic curve that you might see. So anything above here is going to go like that. The curve here in the middle of these two is going to look like that, where it kind of has this asymptote as t decreases in this direction, but as t increases, it has an asymptote in this direction. And remember, we're always looking at, when checking stable or unstable points, what happens as t increases. So that's why negative 2 is stable and 2 is unstable, because the function in between these 2 points approaches negative 2 as t goes to infinity. And then finally, a solution curve below would look like that. And this looks a lot like, if you look up the logistic curve, this is a pretty standard curve used in a lot of modeling. So I'll just finish this up by solving this differential equation. All right. So this again is separable. This integral will be a little more involved to calculate, however. So before I integrate, maybe I'll just do this integral off to the side. So notice this isn't quite an inverse trig integral, but this denominator does factor. And so generally when that happens, we want to use partial fractions. So the method here, we're going to split up this denominator like so. So if you'll recall, we're looking for sort of two separate fractions so that their sum is equal to this fraction that we're actually trying to integrate, because these will integrate very nicely. So if this sum is equal to this, well, remember this means that I get two equations which must be satisfied. A times x minus 2, well, sort of secretly in the form of one equation, b x plus 2 is equal to 1, right? Because when I sum these two, I'd have to create a common denominator, multiplying this fraction by x minus 2 over x minus 2, this one by x plus 2 over x plus 2, and then the numerators would have to sum to 1, so that's where I get this. And so now we know that the x terms, so ax plus bx must equal 0, which implies that a plus b is equal to 0. And here we'd know that negative 2a plus 2b is equal to 1. So this implies that a is equal to negative b. So this means 4b is equal to 1. Which implies b is equal to 1/4 and a is equal to negative 1/4. And that should work out Yes. So we know that this is equal to negative 1/4 over x plus 2 plus 1/4 over x minus 2. And so now we can rewrite this integral as the sum of these two integrals. Which is nice because, again, these are just going to be natural log integrals. Yeah, so fun partial fractions. And so now this is equal to negative 1/4 times the natural log of x plus 2 plus 1/4 times the natural log of x minus 2. And so integrating the right, integrating the left here of then this equation, the integral of dt should just be t plus c. If we wanted to simplify, I'm not quite sure how much my math lab is going to want you to simplify on these. What you could do is first multiply everything by 4. So you'd get 4t plus c is equal to negative natural log of x plus 2 plus natural log of x minus 2. Then you could bring in this negative, so you'd get 4t plus c is equal to the natural log of 1 over x plus 2 plus the natural log of x minus 2. This, you could then combine these two natural logs. And then if you wanted to, I guess you could take both sides to the e. So you'd get x minus 2 over x plus 2 is equal to e to the 4t plus c. A little bit of simplification if you wanted. So yeah, that would be sort of the solution to this. So that wraps up everything on the worksheet. Like I said, if you have any questions about these, please, I will be completely open between 2 and 5 to meet. Just like a normal recitation, I'm happy to go over really anything on the board behind me. So I look forward to seeing you then.